Hello. So while we set up here, our next speaker is a remote presenter, Mahidhar. So he's been a collaborator for the last 15 years. So Mahidhar Tatineni is a great friend, and he's the head of the user services group at the San Diego Supercomputing Center. So he has led the support of high performance computing and data application software on several NSF and University of California funded HPC and AI supercomputers, including their latest Voyager, Expanse, Comet, Garden systems at SDSC. He has varied research interests, particularly in HPC architecture, systems, performance and scalability, benchmarking, and middleware. He is a co-PI on the NSF-funded Expanse system, as well as the National Research Platform projects at SDSC. Mahi, I think I've embarrassed you enough. Are you there?
Yes. Can you hear me okay? Thanks.
Yes, perfect.
Thanks, Hari. And I'm going to share, so that's probably going to knock things out.
It's nice to see you. Yes. Now, if you can go into the presentation mode.
Yeah, let me just, can you see me share okay?
No, I think now I see your screen now. And
let me go into the presentation mode.
So we still don't see it in the presentation mode for some reason. Yes, perfect.
Okay, great.
Thank you.
Hopefully this will stay up long enough. Thanks, Hari, for the introduction. And
sure.
So I'll talk about basically performance of MVAPICH2 on SDSC's Expanse machine. As Hari said, we've been collaborating for a long time with Dr. Panda's group, and Expanse has had MVAPICH2 right from the start, and I'm going to kind of go through an overview of the system and then go on from there. So the machine itself is an NSF-funded machine, a Category 1 capacity system. The PI on the machine was Professor Mike Norman. And then LK, Amit, myself, and Sean were co-PIs on it. It's a Dell machine, basically featuring AMD processors on the CPU side, and on the GPU nodes we have Intel processors and NVIDIA GPUs, and all of this is interconnected with well, now it's NVIDIA interconnect. But so in terms of the machine itself, it's made of 13 scalable compute units at the start, and then we added one industry rack after that. And I'll go into the details of each scalable unit a little bit later. And we have a 12 petabyte Lustre file system in addition to local NVMe storage for these nodes. We've basically aimed the system at the long tail of science, with most of our users running at a medium to small to medium scale, with a few jobs that scale out to a larger extent. Let me go into the architecture itself. So as I mentioned, now including the industry rack, now we have 14 scalable units. That's about 784 standard compute nodes, about 100,000 compute cores. And we have 56 of these 4-way GPU nodes with NVLink on the node. So there are 224 V100s in total on the system. The network is essentially HDR 100 non-blocking at the node level, and then going on into HDR 200 switches, and I'll go into the architecture a little in the next slide. Let me go over there. So in each scalable unit, there are 56 compute nodes with 7,168 cores and 4 GPU nodes with 16 GPUs total. And there's one HDR switch of 200 gig with 40 ports, and then basically we get 200 gig out of each of the ports, so you end up with 3:1 over subscription between racks. A standard compute node is basically two AMD ROM processors with 128 cores, and it's 256 gigs of RAM on each node and a terabyte of node local NVMe. The GPU nodes have 4 NVIDIA V100s on NVLink, and then 32 gig GPUs, and the 1.6 terabytes of NVMe local storage on each. And I talked about the switch going out. Basically, you have 10 times 200 gigs going out from the switch. So that was at the system level. Looking at the processor itself, and most of you have probably seen this already, but just want to go over it in case you're new to it. So it's AMD EPYC processors with 8 core complex dies in each processor, and the CCDs essentially connect to the memory and I/O network through the I/O die, and there are 8 memory channels per node. I'm going to pause a little because I got a chopper going over my head. So we are in the flight path for Miramar, so get this once in a while. So 8 memory channels per socket. It's DDR4 memory at 3.2 gigahertz. And the memory and I/O can be abstracted into separate quadrants with 2 channels and 32 I/O lanes. And I'll show how this shows up in terms of application performance a little bit later in the talk. So each CCD, there are two CCXs, and there are 4 Zen 2 cores in each CCX that share a 16 meg L3 cache. So when we are doing hybrid runs, we try to pack the threads on the same CCX if possible. And the way this is laid out, you can take the 4 logical quadrants of the processor and partition it into different NUMA domains. And this is set in the BIOS. And we run on NPS 4 configuration where there are 4 NUMA domains per configuration. So going to the next slide, basically you have 2 CCDs and 2 memory channels in each NUMA domain. So the memory is interleaved along these 2 channels, and then the PCI devices will be local to one of these 4 NUMA domains. And this is kind of a typical HPC configuration. And as long as your code is running NUMA and is laid out correctly, you can get good performance. So I'll start off with some micro benchmarks. We've been running MVAPICH2 right from the start. I think when we first started out, we were at 2.3.4, and now we have the latest version available on the system as well. Quick OSU bandwidth benchmark just to see internode bandwidth. This is just one task on each node. The message size going up out to 4 meg, sorry. And you can see the bandwidth essentially tops out at I think this is about 98% of peak. So we're doing pretty well there. What I want to focus on more is how things have progressed actually as we started from the initial MVAPICH2 version 2.3.4 out to the 2.3.7 version that's there right now. So I'm looking at the OSU Bcast benchmark here, so the broadcast at 2048 cores, which is 16 nodes on Expanse. And our job size is limited to 4096 cores. So most users will likely not be running at this scale, but we do have some that run at this scale. So you can see that there's a huge improvement over I think this is probably an improvement over a couple of years going from 2.3.4 to 2.3.7. You can see at the small message size, there's almost a 2x drop there. and in the latency. And then as you go out to the large message sizes, it's more like 10 to 15%. But same hardware, basically a improvement of Dr. Panda's group working on the system and kind of optimizing for the processor and getting things cleaned up. And you'll see that for some of the other collectives, this has made an even much bigger change. One example is the all reduce benchmark. And all reduce is there in some of the application codes, like I think WRF and a few others do kind of invoke all reduce a bit. And you can see that there's a big difference now going from MVAPICH 234 out to 237. Both, the latency is cleaned up a lot. Like if you look at the curve, it's a lot smoother with the MVAPICH 237, and it's dropped a lot too. Like even at the larger sizes, you can see quite a big drop in the latency. So that's pretty impressive with the same hardware. And same thing with all-to-all V. Again, this is part of a lot of codes like F50W, and I think even in the Neuron benchmark, probably it's one of the calls that is there. And you can see that at the small message size, there's been quite a bit of improvement even in the all-to-all V benchmark. That's about 20% to 30%, I think. So just from the micro benchmarks, you can see the progression of MPI going from 234 to 237 on Expanse. The other thing I wanted to look at was the GPU side of things. So we have 4 V100s on each node. And I have the topology output here. Basically, you can see that there's NVLink connectivity between all the GPUs. This is a bit different from what we had on Comet, where we didn't have NVLink. So the GPU to GPU on the 2 sockets would have to go through the QPI link. So now it's a lot cleaner. And you will see that even in the intranode benchmark results. And this is a little older slide, but I just wanted to kind of show that there's no real difference between going between GPU 0 and 1, which are on the same socket, and then GPU 1 and 2, which are on on 2 different sockets. This on the left is the latency. You can see almost the same latency between the 2 cases. And the bandwidth curve is very similar. You can't make out what the difference is actually between the 2 sets of runs. So that's doing very well. I just got started with testing MVAPICH2 237, which just came out like a month or so ago. So we are working to test applications with this. We haven't gotten all the application testing done, but early kind of latency benchmark. This is internode, so between 2 nodes looks okay. I think there might be some improvements possible, but with some tuning, but it looks good so far. So so that's kind of at the micro benchmark level. So then I wanted to take a look at how real applications do. Before I jump into that, I just wanted to kind of go over all the applications that use MVAPICH2 on Expanse. And we have, for some of these, we have multiple installations. We have both an MVAPICH2 and OpenMPI installed, for example. But what we found is for some cases, as we scale out, MVAPICH2 does better with some of these applications. So and the codes are kind of varied, right? I mean, you have RaxML, which is a phylogenetics code, QChem, which is a quantum chemistry code, commercial code that uses MVAPICH here. Then AMBER, LAMPS, and NAMD, lots of molecular dynamics codes there. ABINIT, again, a materials code. And then Neuron, which is a simulation environment for a network of neurons. I also kind of listed TensorFlow with Horoward and PyTorch with Horoward. This is typically, most of our users run single node, but we've had a few instances where people ask for scaling out, and so that's one place where I'm going to test out the new MVAPICH2 GDR to see how it does. Oops. So first thing I wanted to do was to kind of look at like layout when you're not using all the tasks. So one thing on Expanse is that we do allow people to run shared node. That is, if you're not using the whole node, we don't charge you for all the node, and we can kind of let other users run on the same node at the same time. But sometimes what that means is you might get lucky and get a clean node where you're the only one, and you get and you're running with fewer tasks than 128. Now, I'm going to show you two examples, one where it makes a huge difference and one where it doesn't. So lamps, basically what I'm doing is running between 16 and 128 cores. So this is just single node. Looking at basically two ways of doing it. Compact, where I'm basically filling an entire NUMA node before going into the next one. And the best memory bandwidth, kind of where I just let it scatter and get very good memory bandwidth. And you can see with lamps, there is an improvement when you have better, higher memory bandwidth per core. Like, I mean, at the low end, about 10%. It's roughly around the 10% range, like between 16 and 64 cores. So keep that in mind. When we go back to the other example, you'll see it's not the same for all the codes. So this is our standard module on the system, and actually it does very well compared to OpenMPI and an implementation of the same benchmark. So here I just wanted to show you what I mean by compact or max memory bandwidth. So in the first case, when I did 16 cores, you can basically you have 2 sockets with 4 NUMA domains each, so you have 8 NUMA domains. So you could stick 2 cores in each, 2 tasks on each NUMA domain, and you would maximize your memory bandwidth in this NPS4 kind of setup. So you can see that layout, or you could just put all of them onto one NUMA domain, which is the compact. So the same thing with the 64. So, but you can see it made a difference about 10% in the case of lamps. This is scaling of lamps going out to 2048 cores. This problem, Lennard-Jones potential with 512K atoms, is a pretty standard benchmark. And what I'm looking at is the time steps per second versus MPI tasks on the x-axis. So you can see it's pretty linear scaling all the way out to about 1024 cores. At 2048, it drops off a little bit. But overall, it's doing pretty well for this. So now comes the other example, right? Like a neuron, which is basically looking at this same kind of setup, but now with neuron. So you have a large scale model of olfactory bulb with 10,500 cells, and then 40,000 steps is what we run this for. So here you can see it's quite dramatic. In this case, the memory bandwidth does make a big difference. So if you let it scatter and get the maximum memory bandwidth, you can see the time for the 16 core case is basically about 3x of the 128 core case, even though you're using 8x the cores basically, or 8x less basically on the cores. So that's a huge difference. So if someone's running neuron in shared, they might get lucky and get good performance once in a while. So there'll be a lot of variability depending on who else is running on the system, on the node, sorry. And it's quite drastic. So you can see here it's almost a 3.5x difference at the 16 core case. It drops off obviously as you fill in more of the cores on the node. This is another case which was one of our acceptance benchmarks. So we have numbers going back quite a few revisions. And you can see at the large, at the small scale, it didn't make too much difference going between the different versions. But as we are going out to the larger scale, 768 cores, you can see that we are improving pretty much, like almost 25% on the performance of the same benchmark between 235 and 237. So again, shows the improvement underlying. And I've scaled this out to 2048 cores, and it scales pretty well. There's actually a little bit of a super linear scaling in the middle, but overall it's scaling pretty well all the way out to 2048 cores. The last one I want to talk about is the RAXML benchmarks. This is kind of the phylogenetics code. This is not a code that scales a lot, but even within a node, you can do MPI and P threads. But even in this case, as we've kind of gone along to the newer versions, we've improved a lot. So like that number you see for Expanse dev was basically the Expanse node, but with the early software stack. And so as we've gone on to the latest versions of, and this I think is both the MPI and the compiler itself being a little bit better. But overall, you can see there's a pretty big jump. It's almost 25% improvement in performance at the 10 tasks and then going out to 40 tasks. Yeah, it's basically around 25% there to like going from 200 seconds to 153. So again, pretty nice. And in this case, I use the compact setup just so that we're not cheating and getting more memory bandwidth, because that gets even better if you do that. So, so that's like a quick look at basically MVAPICH2 usage on Expanse. It's a big system with a lot of compute cores per node, and I think there's been a lot of optimization on the part of Dr. Panda's group in improving MVAPICH over the last few years, and basically done very well. And we keep testing continuously with the newer versions, and basically ongoing testing going with MVAPICH2 GDR 237. There's going to be some applications like Amber, MD-Blue, TensorFlow, and PyTorch that we'll test out. Great. I think I'm done with my talk, and thanks for listening, and open for any questions.
Thanks, Mahi. Let's thank the speaker. Are there any quick questions? I think Danglai.
Yeah. With the applications you have shown, what kind of MPI calls does it use? Like unicast blocking or non-blocking collectives and RDMAs, what kind of
I
MPI
think there are a lot of collectives in both of these, like the LAMPS and Neuron. I think they're all blocking as far as I know. I don't think they've implemented non-blocking in these.
Any other questions, guys? Yes, Bharat.
Wait, Kiri. Okay. Do you have plans to add sharp support on Expanse at any time soon?
I have to look into that. I'm not sure how feasible that is. But yeah.
Okay.
Yes, Arpan.
I was wondering, why do you have Intel processors for the GPU nodes and AMD processors for the compute node?
Oh, okay. So when we started out building this machine like a few years ago, the AMD version of the node from Dell, or I think in general, was not supporting 4 GPUs. So we needed the Intel processor for that. It's changed now, of course. But, but this system was one of the first AMD systems at scale. So there was a lot of new stuff that hadn't been tested out, I think.
Yeah. Thank you. So the reason is, like, when I'm running something on Expanse, I normally don't have enough cores on the GPU nodes because
Yeah.
they are Intel, and I run out of, like, I can't run multiple processes on a single node because of that reason.
Yeah, that there's a limit. It's 40 cores versus 128 cores. So yeah, it makes a difference there.
Yeah.
But for us, I think the more important thing was to have more GPUs per node, because the architecture we had, if you think back to the single switch per scalable unit, right? So we had 4 GPU nodes, and I think the option we had with the AMD setup was to have 3 GPUs per node, which would have given us far fewer GPUs. And in our case, most of the people who use GPUs are running codes that are quite GPU centric and not constrained so much by the CPU, like Amber and the TensorFlow and PyTorch. Usually, the big part of the performance comes from the GPU. So we were just looking to maximize the GPUs at that point.
Yeah, it makes sense, just because, like, I'm running deep learning workloads, and deep learning workloads, we have data loading processes which can go beyond 10 cores per process.
Okay.
And since we have 4 GPUs per node, on each process will get only 10 cores. That's not a lot of cores to do data processing. So yeah.
You probably are also constrained by the memory bandwidth, right, per socket, like rather than the number of cores. I would think the memory bandwidth is probably constraining you also.
Okay. Thank you. Thank you for the wonderful talk.
Thanks.